Symmetry breaking model of volume pulsating walking droplets, a study of critical aspects. In the last 15 years, the classical study of hydrodynamical Faraday waves has attracted renewed interest since the discovery of walking droplets and the more general discovery of hydrodynamical pilot wave models. Notwithstanding that many papers have cleared and rationalized a lot of phenomena with similarities to quantum mechanics, wave-particle duality, discrete orbits, tunneling effect, statistical properties, etc. The study proposes a generalized model describing the dynamics of extended pulsating walking droplets. The first section provides a brief overview of the open problems of walking droplets. The second section analyzes some critical issues of the general stroboscopic models. The third section elaborates on the proposed generalized model of pulsating droplets. Finally, a link is shown between walking droplets and the acoustic gravity wave induced on the surface of the vibrating bath. Introduction. Imagine placing a tiny droplet of liquid on a tray of the same liquid that's being shaken up and down at just the right rhythm. Instead of merging with the liquid, the droplet bounces like a little ball. Under certain conditions, the droplet doesn't just bounce, it starts moving or walking across the surface. This happens because each bounce creates ripples, called Faraday waves, and those ripples push the droplet forward. The droplet's movement is not random, it's guided by the very waves it produces, creating a feedback loop between the droplet and the surface. This phenomenon is fascinating because it acts as a large-scale, visible version of an idea once proposed in quantum physics, that particles might be guided by pilot waves. In the walking droplet system, the droplet is like the particle, and the ripples are like the guiding wave. Although it's not quantum, the similarities allow scientists to explore quantum-like behaviors in a system we can watch with the naked eye. This makes walking droplets a powerful and visually striking tool for studying wave-particle interactions in a completely classical, real-world setting. Conclusions. When a droplet bounces on a vibrating liquid surface, it can sometimes start walking across it, pushed along by the ripples it creates. Our research looks at what causes the symmetry of those ripples to break, giving the droplet a preferred direction to move. We developed a new model that treats the droplet as a flexible object whose shape and volume can change during each bounce. We suggest that each impact creates small acoustic waves on the liquid surface, and their uneven reflections locally change how the bath vibrates, nudging the droplet forward. Recent discoveries of superwalkers, larger droplets that move differently, support our idea that the droplet's volume changes are closely tied to its speed. We believe that droplet volume oscillations not only affect motion but also create hidden energy in the form of acoustic waves beneath the surface, potentially linked to turbulence. We propose that this hidden energy could be measured and might even follow a wave-particle relationship similar to those found in quantum physics. Finally, we suggest experiments to trigger the transition from bouncing to walking by adjusting vibration phases, which may reveal a sharp, direction-dependent shift in droplet behavior. This important article is authored by the following scientists. Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.